Today we want to talk about trigonometric identities. One of the things you want to keep in mind is that running in the background, what you're learning is the unit circle all the way around 30, 45, and 60, and your quadrant angles, their coordinates, associating x with cosine and y coordinate with sine. And now we want to learn those in radians as well. 30 degrees is pi over 6, 45 degrees is pi over 4, 60 degrees is pi over 3, and 90 degrees is pi over 2. So you want to learn those fractions going all the way around the circle. Key thing to remember there is that the denominator tells you what your reference angle is. All right. But while we're doing that, we need to bring up the idea about trigonometric identities. Here's why we care about trigonometric identities. We have all these trig functions. And one of the things that can help us remember how these trig functions work is to remember that all these trig functions are related. So trigonometric identities are relationships between the trig functions. One thing that we always want to remember is that the trig functions are all related in some fashion. This is good. The trig functions are related in a bunch of different ways. This is difficult because the trig functions are related in a bunch of different ways. It's useful because if we forget one, the relationships will reinforce. If we remember some relationships, that will help remind us of other relationships. This is bad because it makes it seem like a lot that we have to know. But it only seems like a lot to remember because it's a lot to remember. And you have to remember all of it all the time in gory detail. Trig identities will come in various categories. So this helps us organize how the trig functions are related. So trig identities are going to come in all kinds of different categories. The first category of trig identity that we want to start to remember are the reciprocal identities. The reciprocal identities are about how we define three most common additional trig functions. So we're familiar with sine, cosine, and tangent. The reciprocal identities introduce secant, cosecant, and cotangent. So the reciprocal identities, we can think of these as being about introducing secant, cosecant, and cotangent. So reciprocal identities are about introducing secant, cosecant, and cotangent. So our first reciprocal identity is defining the function cosecant, which is the reciprocal of sine. Cosecant is the reciprocal of sine. Remember that cosecant is 1 over sine. In words, we would say cosecant is the reciprocal of sine. So in words, we would say cosecant is the reciprocal of sine. In symbols, we write cosecant theta equals 1 divided by sine of theta. So if sine of theta in a right triangle, if sine of theta is opposite over hypotenuse, cosecant of theta will be hypotenuse over opposite. So in a right triangle, if sine theta is opposite over hypotenuse, then cosecant theta is the reciprocal, hypotenuse over opposite. Reciprocal just means flip the fraction over. Reciprocal is a word for multiplicative identity. Sorry, multiplicative inverse. It's what you multiply by to end up at the multiplicative identity. Another important of our important reciprocal identities is secant of theta is 1 over cosine of theta. Secant of theta is 1 divided by cosine of theta. Secant is the reciprocal of cosine. Secant is the reciprocal of cosine. This can be flipped around. We could say that cosine is the reciprocal of secant. That's how reciprocals work. If A is the reciprocal of B, then B is the reciprocal of A. They're reciprocals of each other. Secant reciprocals mean if we multiply those things, we'll end up with 1. So if I take secant and multiply by cosine, I can replace secant of theta with 1 divided by cosine of theta, and then the cosine of thetas will cancel out. That's what reciprocals do. Reciprocal is a word for multiplicative inverse. So when we multiplicate by the inverse, we end up at the multiplicative identity, which is 1. Multiplicative identity, because multiplying by 1 doesn't do anything. That's what an identity element does. Nothing. Cosecant is 1 over sine. Secant is 1 over cosine. Usually when we're saying it to remember it, we say it without the of theta part. Cotangent, that's our third new trig function. Cotangent of theta is 1 over tangent theta. Like we said with the secant and the cosine, when things are reciprocals, they're reciprocals of each other. So this also means that tangent of theta is 1 over cotangent of theta. So we could also write this in terms of tangent and say tangent of theta is equal to 1 over cotangent of theta. When things are reciprocal, we can say that they're reciprocals of each other. This is another way we can talk about reciprocals. They're reciprocals of each other. This means I can also write cosine equals 1 over secant, and sine is 1 over cosecant. Those are also valid expressions of our reciprocal identities. So if we know that the sine of theta is negative square root of 3 over 2, then we can calculate the cosecant of theta by flipping this over. So we would not want to write it this way. We don't want to have fractions inside of our fractions. Notice how we keep the sign, but we don't want fractions inside of our fractions. When we find the reciprocal, we're just going to flip the fraction over. If we take the numerator of 3 and put that in the denominator, then it stays in the denominator. But the denominator of 2 goes into the denominator. It's a double denominator. It goes back into the numerator. It's flip back and forth. So reciprocal is, and if you have a fraction, then we flip it over. Just to remind you of whole numbers are fractions too. But when the denominator is 1, we don't normally write the denominator of 1. So if a cotangent of theta is equal to 3, we're imagining a denominator of 1. So when we flip it over, we have 1 over the 3. Unwritten denominator is 1. An unwritten denominator is a 1 denominator. We usually don't write it because there's only 1, so there's no one else to tell. Take the $3 and split it up amongst the one person in the room. They don't have to tell anybody that they split $3 with themselves. It's like using a turn signal when there's nobody. Any questions? How's everybody okay? So here's one category of trig identity, reciprocal identities. So if we happen to have things in a triangle, let's suppose we have an angle theta, and opposite theta is 3, adjacent theta is 4, and the hypotenuse is 5. Then we should know our opposite, adjacent, and hypotenuse definitions for cosecant, secant, and cotangent. So we know things like sine of theta is opposite over hypotenuse, so 3/5, and cosecant of theta will be hypotenuse over opposite. Sine is opposite over hypotenuse, so the reciprocal is hypotenuse over opposite. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. I can't leave one undone. So tangent is opposite over adjacent. So cotangent is adjacent over hypotenuse. Most important thing to note here is when to use the open for versus the fantastic for or the closed for. It's when there's a C in your trig function. C, closed for, C, closed for, C, closed for. Not relevant in sine and cosine. I'm just kidding. That doesn't make any sense at all. I just happen to write an open for tangent. I don't know why. That's not going to be relevant until the MCU phase 6 when they have a fantastic formula. If they ever get that. Any questions? Comments? Snyder mark. That's category 1 of trigonometric identities. You don't have to memorize these, you just have to remember them forever. In future classes, when you're taking pre-calc or later on when you're taking calculus and you're stuck on a problem and there are trig functions running around, there is an identity that will get you out of it. That is probably the issue. There's some identity that will allow you to rewrite the problem in a different way. So start rewriting the problem using trig identities. Is everybody okay? Everybody looks stoked. Awesome. Category 2. Ratio identities. This is different than the ratios that we had in the reciprocal identities. This is ratios where one of the players is not a 1. So ratio identities relates tangent and cotangent to sine and cosine. So specifically, we care about tangent related to sine and cosine. Spelled sine wrong. The ratio identities give us a relationship between tangent and sine and cosine, and that would also mean cotangent in sine and cosine. Here are the ratio identities. Tangent of theta is sine over cosine. Is the relationship between tangent and sine and cosine. We should have been suspicious that tangent was related to sine and cosine, because sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. 3 trig functions and 3 sides, and we're using them 2 at a time. There's going to be some overlap. So recall that sine is opposite over hypotenuse, and we're dividing opposite over hypotenuse by adjacent over hypotenuse. And when we're dividing fractions, we multiply by the reciprocal. So if we take opposite over hypotenuse and divide by adjacent over hypotenuse, we end up with opposite over adjacent. So tangent of theta is sine of theta over cosine theta. Tangent is sine over cosine. Since cotangent is the reciprocal of tangent, since cotangent is the reciprocal of tangent, if tangent is sine over cosine, then cotangent is cosine over sine. On top of tangent is opposite. On top of sine is opposite. On top. That's how you're going to remember that tangent is sine over cosine. You can also remember that cotangent is cosine over sine. Any questions? You don't have to memorize them, you just have to remember them. Pythagorean identities are about building a relationship between sine and cosine. Pythagorean identities are about building a relationship between sine and cosine. category of Pythagorean identities. There's kind of 9 of them, but there's really only one. Kind of 9, but really only one. Here's the really only one that you need to know. Write this in the other order. Main Pythagorean identity that you need to know is cosine squared plus sine squared equals 1. We usually don't say the of theta when we're remembering our identities in general. Cosine squared theta plus sine squared theta equals 1. Cosine squared plus sine squared equals 1. When I write cosine squared, I mean take the cosine first and then square it. That's the order of operations for that particular symbol. So when we write cosine squared, cosine squared theta means the square of the cosine of theta. We want to avoid writing all these parentheses. We don't want it to look like we're doing the square of theta and then the cosine of that. Here's something that doesn't show up in the PEMDAS. We write cosine squared theta. We mean the square of the cosine of theta. This is the main Pythagorean identity you need to remember. You don't have to memorize it, but you do have to remember it. There are 2 common variations, 2 common ways to relate cosine and sine. Here we have cosine and sine equals 1. We have 3 parts, and the 1 is the lone part. I can solve this for sine, and we can solve this for cosine. So the 2 important variations to recognize are that cosine squared theta is equal to 1 minus sine squared theta. Following the same plan, I could solve for sine squared. Sine squared theta is 1 minus cosine squared theta. These are all just variations on a theme, but we want to be aware about how math works. If 2 plus 3 equals 5, we have to know that that also means that 2 is equal to 5 minus 3, and 3 is equal to 5 minus 2. We want to be able to recognize these things as being related. There are variations on the Pythagorean identity to get, so this is 3, and I said they're kind of 9, but they're all related. Here's how we get another related one. So I take your basic equation, basic Pythagorean identity, cosine squared plus sine squared equals 1, and divide everything by cosine squared. In this first term, cosine squared divided by cosine squared is equal to 1. Sine squared divided by cosine squared is, using a ratio identity, tangent squared. 1 over cosine squared is secant squared. Here is another important Pythagorean identity involving a relationship between tangent and secant. So here's a relationship between tangent and secant, and it can show up in a couple of other different ways. Written this way, secant is all by itself, but I could write this in terms of tangent and say tangent squared is secant squared minus 1. And for completeness, there's another one. Instead of putting the tangent on the other side, I can move, instead of putting the 1 on the other side of the secant, I can put the tangent over there. And we get this kind of weird one where 1 is equal to secant squared minus tangent squared. One plus tangent squared equals secant squared is an important one to remember in your future career in math, and tangent squared is secant squared minus 1 is another important one. That gives us 6, but I said that there were going to be 9, but you could figure out probably how I'm going to get those last 3. I got these previous 3 by taking our basic Pythagorean identity and dividing by cosine, so now I'm just going to go through and divide by sine. Oops. Change the order that I write this normally a couple years ago, but it hasn't taken yet. So if instead of going through and dividing everything by cosine, you can go through and divide everything by sine. In this first term, we have cosine squared divided by sine squared. So through a ratio identity, that's going to be cotangent squared. Sine squared divided by sine squared is equal to 1. And 1 divided by sine squared is cosecant squared. Then we have 2 variations on this. I can solve for cotangent squared as cosecant squared minus 1. Or I could write 1 equals cosecant squared minus cotangent squared. For a total of 9 Pythagorean identities. But really only 1. There's variations on that 1. If you remember how we build all 8 of them off of that first one, then you really just need to remember that first one. That first one you cannot forget. So this one, super critical. The other ones that are important to recognize are these 2 variations and writing secant squared and tangent squared. Those 5 are the ones that you don't want to forget. What we want to notice about these Pythagorean identities is that we have a relationship between sine and cosine, but it's a quadratic relationship. I got to square the trig functions to get this relationship. Or if I want just a first power of cosine or sine, I have to introduce square roots. Introducing square roots makes things messy. But that's one thing to notice about these particular relationships. They're related at the second power, not as the first power. One thing that will help us remember this first one is if we remember our equation of a circle. The equation of the unit circle is x squared plus y squared equals 1. And the coordinates on the unit circle. So x squared plus y squared is equal to 1 is an equation that will give us the unit circle. And the coordinates on the unit circle are cosines and sines of our angle theta. So if this is our angle theta in standard position, the coordinates of this point are cosine theta, sine theta. If x is cosine and y is sine, then cosine squared plus sine squared is equal to 1. Knowing your equation for the unit circle is x squared plus y squared equals 1, knowing that the coordinates of the point of the unit circle are cosine theta and sine theta will help you remember that cosine squared theta plus sine squared theta is equal to 1. You don't have to memorize these 9, you just have to remember them. Forever, starting now. How's everybody okay? It only seems like a lot to remember because it's a lot to remember, and you have to remember all of it, all the time, in all detail. Let's take a pause, come back at 2:15.